The dot product is a commonly used operation in game development. It has two equivalent definitions. For any two vectors with the same number of components, their dot product is defined as the sum of the products of their corresponding components, or the product of their magnitudes and the cosine of the angle between them. We'll label these definitions 1 and 2 for reference. For a quick 2D example, take a equals 3, 1 and b equals 2, 3, where the angle between them is about 38.1 degrees. We see that both dot product definitions produce the same result. In most real-world code, we use equation 1 since it doesn't require knowing the angle between the vectors. But to better understand the geometry behind the dot product, let's take a closer look at equation 2. When vectors a and b each have length 1, that is, both are normalized, their dot product is simply the cosine of the angle between them. Note that this hat notation indicates that these are unit vectors of length 1. For any angle theta, the cosine of theta always lies in the range of -1 to 1. This gives us a normalized measure of how aligned the two vectors are. The value directly reflects the angle between them. In graphics programming, this property is used to calculate the effects of directional lighting. The dot product between a surface's normal vector, or the direction perpendicular to the surface, and the direction toward a light source determines the brightness of that surface. In our game's shader code, we'll take the position of a light, the position of a fragment on the surface, and the surface normal as inputs. First, we'll calculate the normalized direction vector from the surface fragment to the light. Then, assuming the surface normal is already length 1, the dot product between these vectors gives us the brightness value. We'll clamp it to the range 0 to 1 to prevent any negative brightness before applying it by multiplying with the surface color. It's hopefully intuitive that the dot product, and therefore the surface brightness, reaches its maximum when the light direction is fully aligned with the surface normal and drops to 0 when the two are perpendicular. But what can we say about the values in between? One thing we notice is that the cosine function is nonlinear with respect to theta. The naive reasoning is that the surface would be at half brightness when the angle between its normal and the light direction is 45 degrees. In reality, because cosine changes slowly near 0 and faster at larger angles, the dot product only reaches 0.5 when theta equals 60 degrees. In other words, brightness changes gradually when the light and surface are nearly aligned, but falls off much more rapidly as they diverge. We can visualize this concept in terms of how much of the surface area is visible to the light. From the light's perspective, we see that half of the surface area faces the light when theta equals 60 degrees. Therefore, the surface intercepts only half as much light energy as when the light is directly overhead, and consequently appears half as bright. When two vectors are both unit length, their dot product measures how aligned they are, a value in the range of -1 to 1. Now let's see what happens when only one of the vectors is normalized. We can interpret the dot product as the signed magnitude of the unnormalized vector's component along the direction of the normalized vector. This value becomes negative when the unnormalized vector points in the opposite general direction, that is, when the angle between the vectors is greater than 90 degrees. The dot product itself gives a scalar value. To get the corresponding 2D or 3D projection vector of the unnormalized vector onto the unit direction vector, multiply their dot product by the unit direction vector. Note that the dot product is commutative, meaning that a dot b is always equal to b dot a. However, the result can differ depending on which vector is normalized. You can think of the normalized vector as defining a direction, and the other as the one being projected onto it. This concept has a wide range of applications in game development. Let's say we're building a respawn system for a racing game. Players steer their vehicles along a looping track, and if they fall off, we want to respawn them at the closest point along the track's center line. We can represent the track as an ordered list of position nodes, where each node connects to the next by a straight line segment along the track's center. The final node connects back to the first, completing the loop. Let's define a function to calculate the player's respawn point. The function takes the position of the player when they left the track and returns where to place them back on the track after they respawn. It also takes the track data as a parameter. Breaking down the function, we first zip each track node with its succeeding node and iterate over each segment of the loop. Next, we compute how far along the current segment the player was when they left the track. This is the dot product of the player's position relative to the start of the segment with the segment's unit direction. We then clamp the player's position along the current segment so it stays within the segment's endpoints. This is needed because the segments have finite lengths. Finally, we project onto the segment to get a candidate respawn point for each segment, then return the candidate with the smallest distance to the player's position. Now when the player falls off, they respawn at the closest point along the center line of the track. We've explored cases where at least one vector in the dot product has unit length, but what about when neither vector is normalized? We'll come back to that question in a bit. Up to this point, we haven't really discussed equation 1, only noted that it's often used in practice to compute the dot product when the angle between the vectors isn't known. At first glance, equations 1 and 2 look nothing alike, so how can they produce the same result? Suppose we're taking the dot product of two vectors a equal to 0.8, 0.6 and b equal to 2, 4. Notice that a has unit length. We can write out the dot product like so. Now let's turn a on its side. We've now expressed the dot product as a matrix vector multiplication that produces the same scalar result. Matrix A is applying some linear transformation to B. If you're familiar with transformation matrices typically used in game development, such as world matrices, view matrices, and projection matrices, A might look unusual. Typical transformation matrices are 2x2, 3x3, or 4x4, mapping a vector to another vector of the same dimension. By contrast, A is 2 by 1, mapping a 2D vector to a single scalar value. This transformation essentially says, give me 0.8 for every unit of B's first component and 0.6 for every unit of his second component. We can visualize this by imagining a number line defined by A, the one-dimensional space onto which B is projected. The projected value along A increases linearly with each component of B. A change in B0, its x component, always affects the result by the same amount, regardless of B1, its y component, and vice versa. Each component contributes independently to the final value. Visualizing A as a one-dimensional number line is key to understanding the dot product's projective nature. But how do we know for sure that each unit of B0 contributes exactly 0.8 to the result, and each unit of B1 contributes exactly 0.6? Let I be the unit vector along B0's axis, or the x-axis. Since A projects to 0.8 on the I-axis, and both A and I have unit length, we can argue by symmetry that I projects to 0.8 along A's axis as well. A similar argument holds for A1, B1, and J, or the y-axis. In other words, every unit of B0 adds 0.8 to the projection onto A, and every unit of B1 adds 0.6. When A has unit length, it preserves the scale of the space in which B resides. For example, if B0 and B1 are in meters, then A dot B is also in meters. If A instead has a length of 9, for example, then A dot B transforms B into a one-dimensional space where each unit of B contributes 9 times as much, or is worth 9 times as much, as when A is normalized. This case has less geometric meaning, which is why in most game scenarios, at least one vector is normalized before taking the dot product. There are, however, situations where the magnitudes of both vectors carry real meaning. For instance, in physics, work, or the energy transferred to or from an object, is computed as the dot product of a force vector and a displacement vector. We can see this linear transformation in effect with an overlay on our racing game example. Take a moment to digest all of it. Thank you very much for watching. The full article is available on my website, linked in the description below.